Welcome back, everyone. In this video, we're going to be talking more about concavity. We've talked about concavity already in the past. We know that if a function has a second derivative that is positive, then it is concave up. And if the second derivative is negative, then the function is concave down there. Now, the new word for us in this video is inflection points. And an inflection point is where the concavity changes. And so if it goes from concave up to concave down, or concave down to concave up at a particular point, that point would be called an inflection point. And to visualize this graphically, let's look at the following function here. And we can see that it switches concavity at many points, and those points are going to be at B, C, D, and P. And at all of those points, the concavity either goes from concave down to concave up, or concave up to concave down. Now notice that E is not an inflection point because it is concave up on the left side of E and concave up on the right side of E, and so it does not switch concavity at E, so E is not an inflection point, while those other 4 points are inflection points. Finding inflection points algebraically is very similar to how we found local maxes and mins algebraically. And if the second derivative is 0 or undefined at a point, then that point is a potential inflection point. Take the function x cubed, for example. If you take the second derivative and plug in 0, you'll get 0. And if you look at the graph, you can see that there's an inflection point at 0 because the concavity switches from concave down to concave up at 0. Now you might recall with local maxes and mins that if the first derivative is 0 or undefined, that was a potential max or min, not guaranteed to be one. And it's the same thing here. If the second derivative is 0 or undefined, it might be an inflection point, but it might not be as well. And as a counterexample, take the function x to the fourth. If we take the second derivative and plug in 0, we still do get 0. But if we look at the graph of x to the fourth, we see that there is not an inflection point when x is equal to 0. On both the left and right-hand side of that point, it is concave up. It's actually concave up throughout the entire function. And so the concavity never changes, and so there's not an inflection point at 0, nor does this function have any inflection points. And recall that the actual definition of what an inflection point is where the concavity changes, and to really test that, to test whether a potential inflection point is actually an inflection point, we're going to need to check whether the second derivative changes sign at that point. And this is going to have a very similar feel to the first derivative test, just now we're doing it with the second derivative instead. We're going to see where the second derivative is positive, see where the second derivative is negative, and anywhere where the second derivative changes from positive to negative or negative to positive, that's going to be an inflection point. As an example, let's look at the polynomial x cubed minus 9x squared plus 24x plus 5. And we want to find the inflection points of this polynomial. And to find the inflection points, we've got to take the second derivative, and the first derivative is 3x squared minus 18x plus 24, just using the power rule and our other basic derivative rules. And then one more derivative will get us 6x minus 18. And the question here is, where is this second derivative positive, and where is the second derivative negative? So let's take that second derivative and set it greater than 0 and solve that for x. And when the inequality is kind of simple like this, the way that you solve for x is the same way that you would solve for x if it was an equality instead of just an inequality. And so I add 18 to both sides, and then I divide both sides by 6, and I get that the second derivative is positive when x is greater than 3. And now let's do the same thing to find where the second derivative is negative. So let's take that 6x minus 18, set it less than 0, and you solve for x in the same way, and you find that the second derivative is negative when x is less than 3. And so when x is less than 3, the function is concave down, and when x is greater than 3, the function is concave up. And since the concavity changes at 3, there is an inflection point when x is equal to 3. And the overall process of finding an inflection point is always this same idea of taking the second derivative and trying to figure out where is it positive, where is it negative, and at what points does it switch from one sign to the other. Now the algebra you use along the way might be different, but it's the same overall process. And the algebraic techniques are actually very similar to what you used in the first derivative test. And so I recommend looking back at that for cases where it gets a little bit more complicated. And I'll do one more complicated example here, that being finding the inflection points of x squared divided by x squared plus 3. And we've done a lot with polynomials, so I wanted to mix it up a little bit. This is a rational function. And once again, the overall process is the same, but the algebra along the way will be a little bit more difficult. So once again, to find the inflection points, we're going to need the second derivative. So let's first take the first derivative using the quotient rule. And the derivative of the numerator is 2x, and then multiply by the denominator, which is x squared plus 3, and then subtract the numerator, which is x squared, multiplied by the derivative of the denominator, which is 2x. And then you take all of that and divide by the denominator squared, which is x squared plus 3 squared. And I've mentioned in the past that you don't need to simplify your derivatives, and that's still true here, but you might find it helpful to do so. It's going to simplify the process quite a bit. And if you simplify that numerator, you multiply everything out and combine like terms, you're going to get 6x in the numerator and still the same x squared plus 3 squared in the denominator. And this is much easier to take the second derivative of as opposed to what I first got. But now let's take the second derivative, and we're going to use the same technique of using the quotient rule. And the derivative of 6x is 6, and then multiply by the denominator, which is x squared plus 3 squared, and then subtract the derivative of the denominator, which requires the chain rule, and that's going to be 2 times x squared plus 3, and then multiplied by 2x, which is the derivative of the inside function. And we take that and multiply by the numerator, which is 6x. And then all of that is being divided by the denominator squared, which is x squared plus 3 to the fourth. And while this is a perfectly fine second derivative, let's simplify it a little bit to help us out later on. And what I notice here is that those two terms in the numerator both have an x squared plus 3 in common, so I'm going to go ahead and factor that out. And so that's going to get me an x squared plus 3 out in front in the numerator. And I have an x squared plus 3 in the numerator and an x squared plus 3 to the fourth in the denominator. And so I can simplify that a little bit to get rid of the x squared plus 3 in the numerator and get left with an x squared plus 3 cubed in the denominator. And if I take everything that's left, multiply everything out, combine the like terms, what you'll find is you're going to get 18 minus 18x squared. And I can simplify this just a little bit further by factoring out the 18. And so I'm going to get left with 18 multiplied by 1 minus x squared. And you might notice that 1 minus x squared is a difference of squares, and this can be factored into 1 plus x multiplied by 1 minus x. And so my fully simplified form of the second derivative is 18 times 1 plus x times 1 minus x, all divided by x squared plus 3 cubed. And while you didn't need to do this, if you didn't do this, it would be very difficult to accomplish the next step of figuring out where the second derivative is positive or negative. And let's clean things up a little bit by getting rid of everything other than the second derivative that we just found. And as before, the question again is, where is this second derivative positive and where is it negative? And then once we do that, we'll be able to see if it switches sign at any point. And this task is significantly more complicated than the last example, and the technique we're going to have to use is very similar to the technique that you saw in the first derivative video, where really we just need to determine what the sign of this fraction is at different x values. And you might notice that we are multiplying and dividing 4 different things here. We're taking 18 and multiplying by 1 plus x, then multiplying that by 1 minus x, and then dividing by x squared plus 3 cubed. And depending on what x is, it's going to change the sign of each of those different parts, and that's going to change the sign of the whole thing. And trying to keep track of the sign in all of those different parts sounds daunting, but some of those signs are already determined. Take 18 for example. No matter what x is, 18 is still 18, and so 18 is always a positive number. And also look at the denominator, look at x squared plus 3 cubed. If I take any number and square it, and then add 3, that is always a positive number. And if I cube that, it's still a positive number, and so that denominator is always positive. And so really the second derivative is some positive number multiplied by 1 plus x times 1 minus x divided by some other positive number. And that simplifies the process of determining the sign greatly. And so we really just need to focus on where is 1 plus x positive and where is 1 minus x positive. And I'm going to use the same number line technique as you saw from the first derivative video. And we know that something's going to change at -1 and +1. And so I'm going to label those two numbers on this number line. And I'm going to test different values on either side of -1 and +1. And let's start by looking to the left side of -1. And you can plug in any number you want, as long as it's something you can easily compute by hand. And so I'm going to plug in -2 to the second derivative. And the fraction I'm going to get left with is a positive number multiplied by -1 multiplied by 3 divided by a positive number. And since I have 3 positive numbers and 1 negative number, and I'm multiplying and dividing all those things together, the answer there is going to be a negative number. And so I know that if I plug in anything less than 1, the second derivative is going to be negative, so let's label that on the number line down there. Let's do the same thing between -1 and +1. Let's plug in, say, 0. It seems like an easy number. And the second derivative is going to be a positive number multiplied by 1 multiplied by 1 divided by some other positive number. And that's 4 positive numbers, and so the answer there is going to be a positive number. And so the second derivative between -1 and +1 is positive. And you do the same thing to the right of 1. If you plug in something like 2, and you do the same thing, you'll get 3 positive numbers and 1 negative number. And so the fraction there is going to be a negative number. And so the second derivative above 1 is negative. And so the punchline here is that at -1, the concavity of the function goes from concave down to concave up. And at +1, the function goes from concave up to concave down. And so both -1 and +1 are the inflection points of this function.